In this tutorial video, I will introduce SAED3. The current version is 3F. This is a main component in the Landyne software suite for electron diffraction simulation and crystallography analysis. You may download the software suite from the website on the screen. We already explained the installation of Java runtime environment and the Java advanced imaging together with the Landyne software suite in the first video of the series. Please refer to the video if you haven't watched it. If you already installed the Landyne software suite on your PC, you should have the Landyne launcher icon on your desktop. It's like this. I assume you have the software suite installed in your PC. Double-click this icon, you have the launcher set out. This one is the software we're going to use. Click one. If you have a license file, please copy the license key to the Landyne 3 folder. I'll show you in this PC system C and the Landyne 3 program. In my case, I have the SAED3 and the SAED3 license key here. If you didn't have the license key now, you may select the demo mode when you start the program. Let me introduce the functions on the menu briefly and go to details with examples later. For crystal, we have a new for you to prepare new data, and for load is load new data. Remove all is means once you load multiple data there, you can clean out all of them. Exit is to leave the program. In experiments, you can load your diffraction pattern. We have another way to load diffraction pattern is used to drag and drop box. Invert is change the contrast of the diffraction pattern. Erase will clean out the diffraction pattern. You can do some process for your diffraction pattern, resize it, rotate it, or move it. This allows you to move your diffraction pattern, the incident beam, to the screen center. It's very important to do the calibration using this function. So it's called reciprocal space marker. This is a main function for you to find the zone axis of your experimental diffraction pattern. This one allows you to show the diffraction pattern name or not show the name. In simulation, we have two series for you to select. Normally we select kinematic series calculation Occasionally, for a small unit cell, you can select this dynamic theory for calculation. This uses a Bloch wave theory. And you can change the microscope high tension, the high voltage here. Usually we put 200 kV there. You can set up the reciprocal limited here. And this is for the pattern zoom and the intensity scaling. And this is for you to put the index on your diffraction pattern. And this one is special for hexagonal phase. You can change it between to Miller-Bragg index to Miller index. This is deal with the weak intensity special treatment. And this is to show you the lattice only. Sometimes you don't have the correct structure file. You only know the lattice. This function will be useful. In the pattern, first one is the region of interest and the teeth. For you select where, how large area you want to print out. And in the printout, you can set up a resolution for the teeth. And you can select the display as JPEG file or TIFF file. In option, we have a look and feel. You have 3 choices here. And for hide the toolbar for the graphic menu, or you can bring the graphic menu back. In the table, we have a elemental periodic table here. And we also have the space group table here. In the help, we have the current drive here. For my case, now it's a C drive. This is serial number. If you apply a license, you copy this number or take a snapshot of the whole window here and send to us so we can prepare your license file according to the serial number here. The last one is version. The current version is SAED3, and you can find out the update date is here. If we upgrade the software, you find out maybe other letter is here. They're all version 3. The graphic menu bar here are part of the drop-down menu, but it is most often used one, at least here, except for the drop box. It's only appeared in the graphic menu here. Landyne software suite is distributed with a collection of structure files, so you can use SAED3 immediately. Here I show you where the structure file is. Go to this PC, C folder, Landyne 3 structure. Here are all the structure you can use. Now I'm going to show you how to create a new structure file from scratch. I'm going to create a file sodium chloride. New structure. Here it type. And this is cubic and FCC structure with A equals 4.6402. And it's cubic structure, so B and C equal A, alpha, beta, gamma equal 90 degrees. And here the space group are limited here, and it is 2 to 5. Let's check the symbol, and add atom as sodium 1. Atom number is 11. X, Y, Z occupancy is 1. Add, and now change it to chlorine. 1, 2. Atom number is 117, and X only Y is 0.5. Occupancy is 1. So we have a number of atom. Independent atom is 2. In the list is 2. Global isotropic temperature is 0. If you put 1, 2, or 3 here, the high G value, the amplitude will be drop down a little bit. And no notes here. I'm going to save this file. If I click save, the file will be saved. We already have this file, so we're not going to save it. Okay, so the format of the structure file is simple. You can open it in any text editor. Here I show you one. Let's see. Structure and sodium chloride. So you have the title line and the unit cell, space group, atom number, atom 1, atom 2, temperature factor, and this is the notes. And in the notes I write here how to write the file. However, you may have a trouble if you write the format not exactly as required here. So we recommended you use the template to create the new files. We also suggest you to view the structure use SAED3 after you created a new file. The SAED3 is this software, the cubic one. It is very helpful for you to check the structure if it has a problem or not. SAED3 is also provide another function for you to convert structure in other format, for example CIF, and to the format we use here. Let's make the SAED pattern simulation. First thing is load a crystal. Let's try the aluminum. If you don't have the license, you may use the aluminum default. The default setting for the simulation is kinematic theory, and the max scope high tension is 200 kV. And you can see here the default aluminum here. If you load a crystal here, you will have one more file here. You can select the current file as aluminum here, or you can select current file as aluminum default. The following calculation will always use the current file. Simulation is a simple click calculate. You got the diffraction pattern here. Now we may change some parameters. First, the thickness. Default is 300 angstrom. Let's put 100 angstrom here. Do calculate. And you see more diffraction spot come out. Second thing, let's try to change the zone axis. And we change it to 011 direction. See different diffraction pattern come out. And change it again for the 111 direction. 6-fold pattern here. Let's go back to the 001. And now let's try to see if there are small tilting angle here. We put 5 here. You can see the pattern is shift on to the right side. If I put another one here, for example, minus 0.5, see the pattern is the center move to the right side, down right side. Now I change it to the zone axis back to 111. I want to talk about the mass proportion factor here. This value change from 0 to 1. And this is individual phase, the phase you're working on. It would affect the whole overall intensity here. If you have a multiple phase diffraction pattern as a composite in the display, the final proportion should be normalized. Just sum all the individual phase proportion and use the individual one to divide the sum of that proportion. Another thing is this one or this one give you this window is a zoom pattern, the whole pattern, and the intensity is not one phase but all the phase in display. Let's try this. So you can adjust the pattern, the size you want. The intensity, let's try this. Another thing is the orientation here. All of the slide bar, you can change it directly, or you use the mouse point to the slide bar and using the arrow key more precisely to adjust. Now we adjust it to 90 degrees here. So the new appearance of the pattern is shown here. All the pattern can be appeared as a circle as a default, or you can select the disk and change the color to red, and you can change any color you want, and even the user select the color. And here show customized. Let's go back to the black one. That's gray. This is black. If you have a multiple face, you can even show this one in square or triangle just to distinguish them. Let's go back to circle. There's one button called horizontal mirror plane. We'll talk about this later when we do the created the twin structure. All the pattern you simulate here from the current data file, like this one. It can be show or not show here. If you have a multiple, you have a choice. Let's load another file. Let's choose the bismuth and see the list now have a aluminum default, aluminum, and the current one will choose as bismuth platinum. Copy. So this is now a composite diffraction pattern, and the current one is bismuth platinum. We can turn off the bismuth platinum, and now you only have the aluminum show there. See, you can control aluminum file here. Now, the next one is index. If I select index here, it will give me the index of the pattern. There are one more control of the index is here. You can change the color. Now it's in gray, barely to see. You can put it right there. If it's too small, you can change this font size to 18 immediately to see it. And also you can change how many index show up. If you lower the intensity to all of them, and all pattern will be indexed here. Otherwise, you can select the most intense one, or you can only show this is the base of only 2. With this 2, all the pattern can be indexed. And we can show the base vector too. So remove the base vector, remove the base only. The other thing you can show is the first lower zone pattern. And this pattern is 0 lower zone. Let's try how to be a thin crystal. Let's put this one to 100 and remove the index. Let's calculate. But we still now see the first lower zone because the pattern was too big, and also there is another parameter need to be adjusted. Let's change the pattern small. And this pattern is in this parameter in simulation is the reciprocal space limited. And see here is 2, so only a small part of the reciprocal space show up. Let's put a larger number, 5, hit OK here, and redo the calculation. And selected See, now you see outside is the first lower zone show up. Inside is 0 lower zone. And we can turn this off. Why we changed this one usually 2 or 3? Because the larger of the reciprocal limited will calculate using more power to calculate. Usually we don't need that, so we got to change it back to 2 or 3. Okay, here we calculate. And let's try this one. Yeah, so only small part of the first lower zone show up. And besides the index, you can show the intensity too. So this, that will be used the same here. You can change it to show all of them or part of them, or you can show the index at the same time. Let's zoom the pattern a bit large. So index and intensity. Remember, we moved the pattern out of the exactly zone axis. We can put 5, 5, tilt. It didn't change it too much here, but because it's zoom large. But if we put lower center here, you'll find the lower center is actually here. That's because we tilt the crystal away. If we put 0 here and 0 here, recalculate, you will see the lower center now in the center of the pattern. The most calculation work in the SAED3 is carried out in kinematic theory because it's calculated fast, and the work we do here, this theory is give us enough accuracy as we wanted. We do provide a dynamic calculation use Bloch wave method, and this method only applied to relatively small unit cell. And here I use the bismuth platinum structure do example. And here we show is a kinematic theory 200 kV, and zoom is a slight over 1, and intensity scale it put 177, and the zone axis 100, and this one will show you diffraction pattern. Look at this one is pretty weak, and there's a screw exercise here, so you see extinction here. And now we go to simulation theory, selected dynamic theory, and you can see here dynamic theory is selected, and calculate now. And you see that this weak spot and now becomes strong, but still the screw axis is here, and the pattern is changed, and you can change the intensity scale slightly to view the pattern. So the dynamic result, but most of the work we'll do is just using a kinematic theory here. Okay. This one is bigger. You can print the display out, and for this pattern from bismuth platinum, the pattern occupies the whole space. You just go to pattern and save as a JPEG or TIFF. On the other hand, if turn this pattern off and reselect the aluminum and turn the pattern on, and we adjust the intensity and zoom back, it's pretty empty on the side of the pattern. So you can turn the ROI on to show. So the pattern will be printed out just from this blue squares. If we change this one to 400, so only this area will be printed out. For TIFF file, the PPI usually require to 300 or up for a publication figure. So once this done, you can go to Save TIFF, and this is you can change the file name, but we keep it as SAED pattern TIFF. And let's check out. Go here. This is in the result. And we have so many files created before, but this is the one we created now. Double click it. You can show from the photo. That's the pattern you get is a TIFF file. In our file list, you can see here is default aluminum, and this is reloaded aluminum file, and this is bismuth platinum file. I mentioned that we have clean all here, remove all here. That will clean the list. Only the default file will be kept. So let's do it, and you can see this one's still there, and you may need to do it again. So only default file here. So that's, I want to show you what the remove all do. Reload the bismuth platinum file. This is a hexagonal face. And do calculate. Reduce the intensity. Put that here. Put index here. Reduce index to that. Put number to 20. This is the hexagonal face, but the index we gave is a 3-number index. And sometimes for literature, all you want, you can give a 4 index number, and you can transform this from the function called Miller-Blavi index here. This is the 2 here, and we have this one R001 zoom axis, and this is the zoom axis, 3-number zoom axis. You can change it to 4 index zoom axis. And for example, the 110 index, you just put 1, 1, 0 and click here. So this will be full index 1, 1, minus 2, 0. And for the zone X, let's try a different 1, 1, 0. We can rotate this one to 90 degrees. Use the arrow. Enlarge this pattern. And now this is the zone axis 1, 1, 0, and we want to see what is in the full index. Will be 1, 1, 0 here. Make sure that there's space in between. So 1, 1, 0 zone axis will be 1, 1, minus 2, 0 in the zone axis. And let's check this 1, minus 1, 2 index. And let's put here 1, minus 1, 2, and the other side here. So it will be 1, minus 1, 0, 2 index. Sometimes the 3 number index and 4 number index are easy to change, but sometimes it's a little complicated. You can put full index number here, full zone X number here, and transfer them back to back click this one. Very useful tools here. There are sometimes the diffraction spot was so weak that it's hardly find in your patterns. We provide a tool to show the weak diffraction patterns. Here are the weak intensity treatment and the reciprocal space only. So you turn this dialog on. Let's move to the other side. If we put reciprocs lattice only, and this will reveal that this no intensity concern about here, only the lattice here. And if I remove this, there will be the calculated pattern. But there are spots was so weak that hardly to see because the least radius is 0. We can put the weak one, at least give them 3, and you see this one is appeared as very weak spot. And also if you change it at least 1 to 5, you'll see the weak spot you can at least view it. This extinction point will not change it. If I put this one 8, and the very weak spot will increase to 8. Now they put it small, put in 3 at least. But it's your choice to show the weak spot, and or you can show, at least when you teach students, you can show them what is the reciprocal lattice or the diffraction pattern. What's the relation between them? Sometimes some of the diffraction spot was so weak that we want to enhance a little bit and to reveal that diffraction spot is there. So this is give you in the simulation weak intensity treatment, and sometimes you want to show the reciprocal lattice only. Click here. Come here. So this one show you the reciprocal lattice only, and you can see no intensity variation here, only the reciprocal space. And if you turn this off, we'll go back to the diffraction pattern. And those spots were so weak sometimes and hardly to see in the print. and we can change this one to, if this is 0 here, very weak, and go back. If we want to enhance it, see, those were very weak, and I can put 3 here, and you can see that the weak diffraction pattern at least have a 3 intensity come here. You can enhance them to 5, so now this diffraction spots will appear. And if you want the true one, you can put 0, 1, barely to see them. That's the enhance and treatment for the weak spot. And for teaching, that you probably sometimes need to show the reciprocal space and the diffraction pattern, the relation between them. And notice that those are extinction spots. Whenever we change the weak spot, those keep 0 there, will not affect it. So even this one enhanced, this is extinction part, will not show up. SAED3 can also simulate twin electron diffraction patterns. And there are 2 kinds of twins. One is a rotation twin, and the other is mirror twins. And first we show you created mirror twins, and we load the structure of a monoclinic phase is this one, copper oxide. I already load this phase 2 times, and you can see from the list I have a default aluminum here, and copper oxide 1 time, copper oxide 2 times. Why we have 2 times? Because one will be original crystalline, and the other is the twin. And then we calculate each of them in the same zone axis, and you can see the first one show pattern here, thickness 300, zone axis 010, and we also calculate the same pattern, thickness 300, zone axis 010. And now we're going to using the horizontal mirror plane to mirror the diffraction pattern. This line of spots is shared diffraction pattern, and we put this one means the phase copper oxide. The second one will be mirrored. And you can see this is the twin in this diffraction patterns, and this one was shared, and this is the twin spot, and this is twin spot. And you can see how the twin formed by selected one as a disk. So this is a one diffraction pattern, and the other one are we can select it and also select disk, but I will choose a red color. The red color will be including here overlapped, and the red one was. This is created twin by mirror. We use a hexagonal face to show the rotation twin, and here are default as aluminum. Now we come here, load the bismuth platinum here as the first one, and we load it again here. The same phase bismuth here. So you see in the list we have a 2 bismuth platinum here. We choose the first one to make a calculation along the zone axis 001, and we can mark this as a pattern as a disk, but the black one, or let's put the blue one here, and we can come to the second one, bismuth platinum, and the same zone axis 001, do the calculation, and we can make the pattern to disk and select the red one. Nothing show here because it's overlapped. Now we get to rotate this one to 90 degree. So you get a twin structure which have this 2 unit cell 90 degree relations and diffraction pattern like this. If we want to show all of them in the black, you probably see this pattern in your real experimental diffraction pattern. We can also simulating the composite pattern for two-phase have a fixed orientation. One example is for in the bismuth platinum system. One is bismuth 2 platinum triangle phase, and the second one we load is a bismuth platinum hexagonal phase. And first simulate this one in the 001 direction, and we show pattern here. Diffraction pattern like this, and the second phase we're simulating the same orientation, 001 direction, and show the pattern like this. And just notice that the original pattern here angle should be 0. So when you just load this 2 pattern and simulation, this the diffraction pattern will be like this. But the experimental results show there are 30 degree angle difference rotate from each other. So the second phase will be 30 degree rotate needed. The true pattern will be look like this. If we put a disk here, and so this is one thing. And we noticed that also I adjusted the mass proportion. Original this bismuth platinum phase is proportion is 1 will be like this, but experimental observed that this pattern the intensity is rather weak, This will be the second phase, so I had to drill the mass propagation getting small. This looked like a fit to the experimental patterns. Let's bring the first phase to the black disk 2. Yeah, the diffraction pattern would look like this. So there are very small amount of bismuth platinum there. The main phase will be the bismuth 2 platinum phase. And here I show you how to find the electron diffraction from 2 phase. We can have a fixed orientation. Now we go to a new topic to study the experimental SAED pattern. First, I'll show you how to load the experimental pattern to the program. We have a traditional way to using window file system. And click experiment, load the follow the, go back, this one in the experiments, and SAED3 C used to be, and this one is copper 2 sapphire, and you have the pattern here. And now I'm going to clean the pattern. The other way will be more easy. Just go find your pattern first. The pattern is in C pattern, C folder, and then 3 experiment here, and this pattern we just drag and drop to this box. The pattern will automatically load it. After we loaded the experimental electron diffraction pattern, we can do several processing before we do the find the zoom axis. Under the experimental, we have invert EDP and grayscale. We have a resize rotation, and also center the EDP. Let's do the first. And you can see the experimental pattern we loaded a little smaller than the display size. And we can cover this one. This is controlled by the grayscale. Now is 255, and so it's bright. So it's white. And if we change this one, we can make them just the same grayscale as your patterns. So this look like the pattern are full in your display area. If you want to invert the experimental diffraction pattern, you can click here, invert the image brightness. So the image come to bright, but your cover is now black. So we can change this one to white one. Almost the same grayscale as your pattern, so make that almost full. And there are other things we can do about it is the resize one. If we want to resize the sample, we can also cover the display area. Just make them slightly larger. You can see this point now come to the edge, or even larger. That will be disappeared. And if your pattern, original pattern is big, and you can shrink the pattern to small, that's also possible. And you can also using the key arrow to do that. If you want to somehow to rotate your pattern, you can do that too. So we put the rotation back to 0 degree. If we don't want to rotate them. And the final one is moving. This is the incident beam's position. We want to move the incident beam to the center of the screen, and they come to this one, the shift and center, or in the experiment, shift and center. Move this one to here. And you can see you can only show circle, or you can only show the cross lines. And you can decide how many circles here and how many lines there. Now it's 8 lines of them. So once you have this line or circle appeared, you can just point to the center, and also the mouse left the button and drag the image and release. So hold on and drag them and release. And in that way you can see the symmetry spot all in the same circles. Try to see that. And like this one. Look like this one. The same shape as this one. And if we can move a little bit here, or up a little bit. Yeah. Once you click this pattern again, you cannot move anymore. This is already in the center. Then we're ready to do the calibration and find the zone axis. It's very important to do the calibration before we carry out to find the zone axis. Usually your diffraction pattern have a scaling bar, so you know you can measure from your incident beam to any of the beam. For example, from this one to this one, I measured is 2.95 1/4 nanometers, and from the central beam from here to this one is 3.7 1/4 nanometers. And so this way we'll do the calibrations. The other way, you can move the whole pattern of your scale bar on the left side to the center, so on the end of it the scale bar is, you know, the value you can put in. So let's do it now. To go to reciprocal specification marker. So you can show the circle here, and also we know, like the first one I said is 2.95, and I selected, no, it is 2.95. And here I selected is 1/4 nanometers. And I update. This is 2. So it's 2.95 update here. So it's pretty small. It's now covered to distant to here. So then come to the calibration part, and the pattern size here. We had to zoom this one, or here. We had to zoom here. Over here. So this one will show 2.639, and the circle cover to here. So we got here, we measured is 2.95, 1 over nanometers, and then we, after we zoom the pattern, use this value, we get the correct circle size. So we do the update here, and that's do the calibration. Find the zone axis means we know what the phase is and we took a diffraction pattern, but we don't know which zone axis of this pattern is. And in this experimental pattern we know is a crystal from load is copper sulfur. And this one copper. Yeah, we got the load sample copper 2 sulfur, this one. And then we had to measure the, go find the zone axis. And here is the update for the matching factor. And warning you if you change something, yes. We will copy this value the same as showing the zoom patterns here is 2639. And then we can display the two vectors we just selected. Click here. There will automatically 2 vectors here, but we need to point out the nearest one, like this one and this one, for us to find out. Now first to the angle to this line, and we need to shrink the pattern. You can fill the certain value directly here, and this is 88. You can fill the 44. Click here again and increase smaller. Not necessarily this one is fixed, but you have all this line of the marker, so to fix to that line approximately. So increase. Try your best to fit in. Yeah, this will be my best to fit in. All the markers are filled in this line. So we find that the second line will be to this one. So then I decrease my angle. Increase a little bit. A little bit. And this value now is 100, is about 50 here. But I can put 50 here. Increase. And now, since I need to decrease a little bit here. Now is the best fit for this line too. So we got to find the 2 basic vector here, and we also have this tolerance factor 5%, and then we got to find. We find is the zone X is 211, and we found this zone X is based on the angle and also the basic vector. We also need to furthermore to check the diffraction pattern from this one along this 211 zone axis. Are the intensity match or not? Let's put this one here on the 211, and I copy and I put into right, and now I can get rid of this calibration. More circles, scale circle now show. Because the pattern are not tilted correctly, I need to reorientate the pattern. And it seems that perfectly matched with the pattern, with this pattern, with most of the intensity here, 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 and also the lattice also match well. I can put a disk here to show you, and a circle here to show you. So it's a perfect match, except this point, and it could be because the simulation just approximately to match the factor of this one. But it's good, this one also matches good. So this zone axis must be 211 zone. And we can also say here the total fixed number is 6. You can also try other zone axes, and they all match with the letter, but this 211 we test here, it's matched perfectly well. This is a zone axis. If you want to index this pattern, it's easy. Just go to index and show the index here, and we get the index we can show in blue, and we can get a big number here, 24. And now it's only index the most intense one, and I can reduce the limitation of the intensity, and you get all the most intensity pattern are indexed. Yeah, so all the most intensity index. Or you just simply go to the basic one. So we got this one is indexed, and also this one is indexed. And inside of this one will be this reverse. And we got some number here, -1. And I can show you maybe in yellow or other colors will be. Let's try to go to yellow. See if this one will show you a little better with 0, 1, -1, and this is 1, -1, -1. So you can see that one. That way we find the zone axis and the index for unknown pattern, but we know which phase it's from. Thank you for watching. Please check our other video about Landyne software suite for electron diffraction simulation and crystallographic analysis.